Seabiscuit in this particular clip. It's 0, right? Remember, going back to our displacement, is not a distance that's traveled. Seabiscuit has actually traveled about a mile, right? I think those tracks are a mile in circumference. But if you start at one point and then you come all the way back around, then that gives you a displacement of 0. So if I start, here's my horse, if I start here and then I travel all the way around and come back to the same position, my initial position is equal to 0, my final position is equal to 0, so my displacement is also equal to 0. Right? So displacement is not the same as distance. We'll see that. Actually, displacement is what we'll call a vector quantity, and distance is what we'll call a scalar quantity. But I'll define that in just a moment. The other reason I want to show that is just, you know what, sometimes when you're taking a course like physics or any other course really, sometimes it's useful just to work with somebody else, I find. Especially if it's somebody that's just a little bit better than you at the material, or maybe even a lot better, like a tutor in the tutoring center. Have I told you about the tutoring center? Or somebody in this class that you know is a good student, and you trust them, and you trust that they won't lead you astray, or even me, right? Y'all can come see me. That they can sort of give you a goal to reach and help you along with that, and just, you know, give you somebody to chase after, and that makes you often go faster, I find. All right. So let's look at this. This is a number line or a position graph, 0 here in different directions. My displacement, let's say that I start here and I go here. I go from 1 to 4. What is my displacement in that case if I'm going from 1 to 4? It's going to be 3. My final position is 4. My initial position is 1. So it's going to be 3 meters. In fact, I don't write it there, but I'm going to write it as plus 3 meters. Now let's say that instead of that, I go from minus 1 to 2. What is my displacement in this case if I go from minus 1 to 2? It's also going to be 3 meters. So I define this as x final minus x initial. This is x final. This is x initial. So that's going to be 2 minus negative 1. These become positive. So that becomes 3 meters. Okay. Now let's imagine that I'm traveling from, say, negative 2 to negative 4. What then is my displacement in this case? It's going to be negative 2. That's right. So I go my final position, which is negative 4, minus my initial position, which is negative 2, and that's equal to negative 2. Here, this negative represents a direction. And the reason that we include direction for a displacement is what displacement is. It's a vector quantity. And vector quantities have both magnitude and direction. Magnitude is just the value. So if I'm looking at this vector, negative 2, this is a displacement, it's in meters. The magnitude of this vector has what value? You'll think for just a second. Now, what is the magnitude for this? It's going to be 2, right? And the direction is in the negative x direction, or the negative y direction, or what? It's negative x here, I suppose. So if I have delta x equals negative 2 meters, my direction is in the negative x direction. Turns out that's going to be to the left, because of just sort of the way we define coordinate systems. And then the magnitude is going to be 2. Now in the next chapter, we'll define vectors in different ways, because we'll deal with vectors that are not just in 1 dimension, but in 2 dimensions. Fortunately, this chapter is not terribly difficult, although it can be difficult, because our vectors are just in 1 dimension. Sometimes we'll give direction in other ways, such as we'll give north, south, east, and west. So say, for example, I have a compass rose. Never, what are you never supposed to do? Yes, y'all say that too. Never eat sour watermelons. Does anybody say never eat soggy waffles? Yes, just you and me. Right, is it Mariah? Bridget. Where's Mariah? Mariah in this class? No, that must be another one. I'm sorry. All right, Bridget. Yeah, never eat soggy waffles. So that's never soggy eat waffles. So we can do northeast, south, west. We can give cardinal directions. So say, for example, when we see this next chapter, if I have a vector that is, say, 30 degrees in this direction, then we would say this vector is 30 degrees north of east. We'll get into that next chapter. Or if I have a vector over here, we would say it's north of west. If I was here, what would my vector be? South of west, and over here, south of east. There are different ways that people do that, but that's the way we'll do it. Not till chapter 3, though, okay? So don't sweat that right now. Right now, we're just dealing with plus and minus for vectors. Some things that we have that are our vectors: displacement, velocity, and acceleration. Those are all vectors: displacement, velocity, and acceleration. Some other things that we'll deal with in chapter 4, we'll get into forces. Those are vectors. And then also momentum is a vector that we'll deal with in chapter 6, I think. We usually show variables with vectors with an arrow. So for example, if I have my displacement, I'll show it with an arrow over it. I get kind of lazy with this, especially as we move along and we get into sort of word problems. But we'll always be generally when we're talking about position, we'll talk our displacement, we're talking about the vector quantity. That includes the direction. Okay? You'll see, you'll get the hang of it. Scalars, on the other hand, vectors have magnitude and direction. So scalars are only going to have what? Direction? Right. They only have a value. They only have a magnitude. These are quantities that have no direction. So think in your mind just for a second. What are some scalar quantities that you know? These are quantities that will not have a direction attached to them. So just think before you speak and think, gosh, what are some scalar quantities that I know? All right, now what are some scalar quantities? Speed is a scalar quantity. We'll talk about that. Speed is actually a scalar quantity that's associated with the velocity. So velocity has magnitude and direction, but speed is just the magnitude. Good. What were some others? Length is one, like if you're measuring a measurement on something, you know, Jacob. Time is a scalar quantity. What are some others? Mass is a scalar quantity. That's right. In the back. Okay, yeah, volume. You said that. Oh, yes. Volume is a scalar quantity. One other one. Charge is a scalar quantity. We'll get into that, but that's not one I wanted, but thank you. Temperature is a scalar quantity. Right. It's actually not hot in here. But there are lots of different scalar quantities. Time, mass, length, or other dimensional measurements. Charge, we'll get into that next semester. Speed. Remember, speed is, as I said, it is the magnitude of the velocity. So if you have the velocity information and you strip away the directional information, that would be the speed. There were some others. Oh, temperature. I think y'all said one or two others, but we'll just leave it with that. All right, let's try this quick test. Which of these is or are scalar quantities? And I'll show you this question just because I like questions like this, sort of get you acclimated to them, or I give you 3 or 4 or 5 options, and one or more of the answers is correct or incorrect, and you have to pick the right combination. All right, we'll stop at 28. 28. Just 3 more seconds. Awesome, C is right. Just want to remind you with the clicker questions, I mean, there almost everybody got right, but if you're not getting a lot of clicker questions right, No need to freak out, okay? That's okay. That's what clicker questions are there for, in order for you to sort of get things wrong and learn from your mistakes. You're allowed to miss a bunch of clicker questions and still get the full maximum credit allowed. Somewhere between exams 3 and 4, y'all are going to start to max out that credit, and I'll sort of let you know when that happens. But that's what it's there for. It's to help you sort of keep your thought, your brain engaged as we go through this material. Okay? Not for you to stress over. What was the answer? C, right. Mass and speed are both scalar quantities. Acceleration and velocity are vector quantities. Let's see. Why does the gingerbread man, don't write this down, but why does the gingerbread man never wear shorts? Why? Because he has crummy legs. Right. Okay, so velocity and speed. We said this, but let's just put it in words. Speed is a scalar quantity. It is the magnitude of the velocity. We'll also define something called average speed. Average speed is sort of what you think of when you think of speed. It is the distance traveled divided by the time. Or we can just write it as d over t. But we'll have several different types of velocity and acceleration, so you have to keep them straight in your mind. So that's our average speed. It's just distance traveled divided by time. So if a runner runs a 400-meter track in 60 seconds, what is her average speed? Well, how would we find that? All right, we just say 400 divided by 60. The distance covered is 400 meters. So we'd say 400 meters divided by 60 seconds. And again, we're dealing with somebody that's running around a track. Runs 400-meter track. So that is approximately equal to 7 meters per second. So about 7 meters per second for a decent 400 time. And then what is the displacement for this lady? 0, right? Because you begin, x initial is 0 and x final is 0. So the displacement, which is a vector, is going to be 0. Okay? Average velocity. Average velocity we're going to define as the displacement divided by the time. Notice how this is different from average speed. Average speed was the distance over the time. Average velocity is displacement divided by time. Velocity is a vector. Speed is not a vector. Displacement is a vector. Distance is not a vector. Distance is like what your odometer reads, right? There's no directional information for that. Distance is a scalar quantity. Average velocity is a vector with both magnitude and direction. So if we were to think about the runner in the previous problem that runs at 60-second 400, what is her average velocity? It's going to be 0, right? Because she goes around and begins at the same point. Begins and finishes at the same point. So our average velocity is going to be equal to delta x over delta t, which is going to be 0 minus 0 divided by 60 seconds, or 0 meters per second. That is our average velocity. That might seem kind of funky, but that's just sort of how we define displacement and average velocity. You could see some basic problems on the test about finding the distinction between speed and velocity and displacement in that way. You're definitely going to see some questions where you have graphs and you have to analyze the graphs and figure out what is the velocity or the acceleration or the distance traveled. And I'm going to show you how to do that. But first, let's look at this plot of position versus time. So what I've plotted here is the x position. This is not displacement. This is the position at a particular time. So at time t equals 10 seconds, the object is at x equals 0 meters. At time t equals 20 seconds, it's at 20 meters. So it's a plot of x position versus time. In graphs, we can find a couple of things, and we're going to be doing both of those things. We can find the derivative of a graph, which is just a fancy way of saying what? The slope. So we can find the slope of a graph. You should know how to find the slope. I'll show you, but it's, how do you find the slope? Right, the rise over run. So this graph, you have a run of 30, a rise of 60, so the slope is going to be 2. So you can find the slope of a graph. You can also find the area under a graph. Our fancier way of saying that is to say what? The integral of a graph. So you can, the integral, where's my mic? Y'all still hear me right there? Okay. Test. Just a second. All right. What was I saying? Oh, the fancy word for area is what? The integral. Y'all get to that in the very end of calculus. Many of you are in calculus this semester. You'll get to that at the very end. When you do an integral, you're just taking the area under the curve. Now, in this particular case, the slope of the line, or the derivative of the line, gives the average velocity over the interval from, well, if we're going over the full interval, from t equals 0 to 30 seconds. All right, remember average velocity. You've already written this down. Let me write down is delta x over delta t. And so if my time interval is 30 seconds minus 0 seconds, my final time is 30, my initial time is 0, then that means that my position is going to be 40 up here minus negative 20. That would be my displacement over that 30-second interval. So I'd have 40 minus negative 20, which is going to be 60 over 30, or 2 meters per second. That's how we would calculate the average velocity. We would find the position up here, which is going to be 40. We would find the time here, which is 30. We'd find the initial position, which is negative 20, and the initial time, which is 0. Or we could just say, what is the slope of this line? And they'll give you the same answer. They are the same, in fact. We'll have some more questions about that. Now, in this case, because the line is linear, that means it's a straight line. And because of that, because the line is linear, that means that the velocity doesn't change. And the average velocity, say, over another time interval, I don't know, say from 10 to 30 seconds, that's going to be exactly the same. Instead of writing that out, well, I'll write it out here. So I'm going to go back to the graph and show you that. Between 10 and 30 seconds, that's going from here to here. My position at 10 seconds is 0. My position at 30 seconds is 40. So that average velocity is going to be 40 minus 0 over 30 minus 10, which is equal to 2 meters per second. So notice that no matter what interval for this line that I use, the average velocity is going to be the same. But that's only because, why? Why is that true? No matter the interval I use, the average velocity will be the same. because it's linear, it's a straight line. If it was not a straight line, that means it's changing slope, then that's not going to be true. And we'll see some graphs where if they're not linear, they do change slope. All right, so like this graph, for example, here my average velocity is going to depend on the chosen time interval. I can choose different time intervals, and I'll get different average velocities. So let's say, for example, I want to know the average velocity from 0 to 10 seconds. To do that, I would take the point at t equals 0 and the point at t equal 10, and I would want to find the slope between those 2 points. Or I could say, well, my final position is 30, my initial position is 20. So I'm going to have x final minus x initial over t final minus t initial. X final is 30 minus 20. That's divided by 10 minus 0. It's going to be 1 meter per second. That would be finding the average velocity between these 2 points. But if I say go from 10 to 30 seconds, I'm going to get an entirely different average velocity. Because you see, as this object, which is described by this graph, as it moves through space, it changes the slope of this graph. That means it's changing its velocity. It's changing the speed at which it's traveling. So if I go from, say, 10 to 30 seconds, this now is going to become my initial position. And this is going to become my final position. So my answer is going to be the slope of this line. And that bears itself out in the equation. But the answer will be the slope of this line. Now, first of all, before we move it further, just want to make sure you understand that I can determine the sign of slope just by looking at the line. I know some of you haven't done that, or you might not be familiar with that. But this red line, does this red line have a positive or negative slope? Okay, it's positive. And the blue line is positive or negative? Negative. All right, so what if, and then what about a line that looks like this? What is the slope of that line? 0. So I have a positive slope, a negative slope, a 0 slope. What about this line? It's undefined because it's an infinite slope. It's like 1 over 0, so it's undefined. You okay with that? Okay, awesome. Okay, so from 10 to 30 seconds, you might have already done this, but it's going to be minus 20, that's my final, minus 30 meters divided by 30 seconds minus 10 seconds. And that's going to be minus 50 divided by 20, or minus 2.5, or actually it would be more correct to say minus 3 meters per second. Okay, notice it came out negative, and we know that it should be negative because of the way it looks on the graph. Okay, y'all with me? It'll get more difficult. I know some of you are like, oh, why are we going through all this? And some of you are like, ah, and either one's okay. It's going to be okay for both of you. Okay? Now let's look at instantaneous velocity. This is going to be the bulk of what we'll use. So you'll certainly see average velocity on the exam. I'll either give you a graph or I'll give you some data and ask you to calculate the average velocity. And I'll show you some problems. We'll work through something together. So let's look first at instantaneous velocity. It's the velocity at a particular time. In fact, at a particular instance, at an instant. And that's why they call it, instantaneous, because it is the velocity at a particular instant in time. Okay? A speedometer in a car is the magnitude of the instantaneous velocity. It is the velocity at a particular time, and your speedometer gives your speed at a particular time. We can define the instantaneous velocity in this way. You don't need to know calculus, but it is useful to look at it in this way because many of you have seen this or are beginning to see it. The instantaneous velocity is the limit of the, gosh, what is this? This delta x over delta t. We've already defined this. What is that? Not just any velocity, it's the what kind of velocity? It's the average velocity. So remember, this average velocity is the velocity over a particular time interval. But the instantaneous velocity is the velocity at one single instant in time. So what you do here is that you take this average velocity and you let that delta t, which for average velocity was really big, or over a particular interval, you let it get really, 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 really small. You let that delta t approach 0 at a particular point in time, and then that defines what is your average velocity, your instantaneous velocity. The limit of this, as this gets really small, as delta t gets small. And that is the definition of the derivative. Y'all know who invented calculus? Have I told y'all this? Nobody knows? Who invented, or who came up with the laws of motion? Newton, right? See, everybody knows Newton because he came up with the laws of motion. He described how things move in the laws of motion. But he also invented calculus. And in that way, he changed your world in every conceivable way that you can even imagine. Okay? Not because calculus sucks and you got to take the class, but because this building would not exist without calculus. These projectors and your little cell phones and your water bottles and practically everything that touches your life in ways that we know are because of Isaac Newton's invention of calculus. Just take a moment and think about that, because it allows for science and engineering and the study of nature as we know it through calculus. It describes how things change, and in nature things often change. He invented it. Who said what now? Right. Did he tell you about Leibniz then? So there was another person, he was a contemporary of Newton, who also invented calculus, or came up with calculus, or however you want to describe it. What does he say? Invent or discover? I think invent is probably a better term.
Oh, wait, Dr. X says discovered.
He says discovered? What does he know? He's just a mathematician. But anyway, there's another guy that invented it or discovered it, whatever you want to say, at almost exactly the same time, and they were separated by countries. They didn't know one another. So some people say that at particular times in history there were just discoveries ripe to be made, and that calculus was one of those. Okay, so in a nonlinear graph such as this one right here, the slope of the tangent line is equal to the instantaneous velocity. So this is our instantaneous velocity. The tangent line, you'll get the hang of this, but the tangent line is a line. Like let's say, for example, I want to know what is the tangent line here. It's a line that sort of balances on that function. I like to think of it as a seesaw. There is a mathematical definition that every point has to be like equal distant from the function as it moves out along that line. But don't worry about that. I just sort of like to think of the tangent line is tangent to the curve, or it's like it balances. You can see it better if it's a circle. Like if I have a circle like this and I want to draw a tangent line, I want to draw the tangent line like that. It's like it balances on that function. You'll need to be able to draw tangent lines, and we'll do some practice in class for that. But the slope of this tangent line, this is equal to the instantaneous velocity. It'll be both the magnitude and the direction, because the slope will have a positive or negative value, and that will give you your direction. It looks like we have a quick test on the next page. May I go down from here? Okay, here's a graph. I know not everybody has your book, but just do your best on it. I want to know, what is the instantaneous velocity at t equal 4 seconds? At t equal 4 seconds, what is the instantaneous velocity? In order to do so, you need to figure out what is the slope at that point. At t equal 4 seconds, at this point, what is the instantaneous velocity? Y'all see it okay in the back? Not sure, ask your neighbor what they put. I know a common mistake that some of you are going to make, and I already see it on some of your answers, is that some of you, when you're doing your rise over run, your slope of this graph, you're not going to go by the axes. Instead, you're going to count the squares. And when you count the squares, you'll just divide the number of squares by one another. And that's not correct. You always go by what's on the axis. Because notice, here a square is 1 unit, but here a square is a half a unit of time. So make sure that you're aware of that. For the exam, too, because it's just, once you do it enough times, you'll get used to it. Don't count the squares. All right, we'll stop at 1:55, 10 seconds. $1:55. Okay, A is right. Very good. You draw a tangent line. So there might be some judgment call, but I'm going to draw it. Something like this. And then I just do rise over run. I draw my triangle, or however you want to do that. I notice that this side has 2 units, 2 seconds, because I'm going from 3 to 5 seconds, even though there are 4 squares. And then here, I'm going from -3 to 3, so that's 6 meters. And then I do rise over run, and it's 3 meters per second. Notice that on this one, you could have immediately gotten rid of D and E right away, because those are negative or 0, and you know that that slope is neither negative nor 0. By the way, what would it be, say, right here at 2? Don't think about it. Don't write anything down, but just think about, what is the slope at 2 seconds?
0.
It's going to be 0. My tangent line here would be right here, and then I'm not sure this is right, but if this was one of the right answers, what would the slope here be? It would be negative. I don't know if it is negative 2. It looks pretty close to 2, but so often on tests, what I'm saying is that you can just look at the answers and figure out which of these are inappropriate. Not like inappropriate, you know, but which of these are incorrect because they're negative or they're 0 or a number of other reasons. Yeah, Chandra? Why did I do 5 if t is 4? Oh, good question. So she asks, why do I use 2 seconds here? Because I go from 3 to 5. If really I ask for t equal 4. What I'm asking is for the instantaneous velocity at t equal 4 seconds. So what is the velocity at that particular instant? In order to find that, I have to find the slope of the line at t equal 4 seconds. And so what I did is I drew a line, and it happened to come down to 3, and it happened to go over to 5 seconds. I drew a line from here to here, a line that's tangent to the function. Okay, it's like it's balanced on that function. In this case, it pretty much follows the red line pretty well. And then I find the slope of that line. So the 3 and the 5 that I use I'm just using those to find the slope. Alright. The 4 is the actual instant that I want to know the velocity. Other questions, y'all? Did I answer your question? You sure? Alright. Let's try another one. I'm going to write the options up here. I know not all of you have everything yet. But I want to know what is the average velocity between t equals 0 and t equal 2 seconds. And your options are going to be -2, -1.5, -1, -2.5. I'll go back up to the graph and let me clear it out for you. What is the average velocity? Is it A, -2, B, C, or D? These are all in meters per second. I'll start these clicker base. What is the average velocity between t equals 0 and 2 seconds? Okay, folks, I'm going to stop at, say, 105. Just guess if you're not sure. Ask your neighbor what they put. 105. So a couple more seconds. Very good. B is the right answer. On this, I'm not finding the slope of the line. Instead, I'm just pulling the data off the graph because I'm looking for average velocity. Especially on this one, where it's a non-linear graph, I really have to be careful about just pulling the initial and final points. Now, in this particular graph, it's actually pretty linear between 0 and 2 seconds. So if you found the slope, you might get the right answer. But if I asked you for the average velocity between, say, 0 and 3 seconds, the tangent line will not give you the right answer because there's a lot that goes on in between those two times. So at t equals 0 seconds, I want to know V average. It's equal to delta x over delta t. My delta t is going to be 2 minus 0 seconds. At 2 seconds, my position is minus 4 meters. At 0 seconds, my position is minus 1 meter. So minus 4 minus -1. So that's minus 5 over 2. Which is minus 2.5. Is that what y'all put? It's 3. It's 3 over 2. You're right. Yes, thank you. Yes, you're right. Thank you. So it's minus 3. So that's minus 1.5. My problem was I was not making this positive. I should have. Okay. So that's going to be minus 4 plus 1, which is minus 3, divided by 2 minus 0, which is minus 1.5. So B is the right answer. You'll definitely have some problems like that on the exam, where I give you a graph, you have to find things about that graph. We still have a couple more things that we'll do regarding that. For now, let's go and do some of these clicker questions. And by the way, I'll put up the solutions for chapter 1. And if you have your workbook, these questions are in the back. There's like an appendix in the back that has all the tests as well as the questions. If you want to follow along there, that's fine. And then also just before we get too close to 11:45, the end of the class, I just, right? You already with me. 11:45, the end of the class. 1140, right. Now, I've been working here for like 11 years, and I've always had a 4-amp class, and you would think I still get confused about when it starts and when it ends. Actually, I get when it starts okay, but I always think it goes to 11:45. I'll get it one day. But remember, there's what on Wednesday? Like a huge pizza party in here? No class. So there's nothing. Nobody, if you come in here, nobody's going to be here. And you're going to walk in, it's like, hey, what's up? Likely today or tomorrow, let me show you this actually before we do this. I will send you a link, and I'll probably have you go on the website, and I'm not going to have you do a whole lot, but if you go on the website, probably have you watch a few of our screencasts for my online class. I know that's not terribly exciting, and it's not going to be like a whole class worth of material, but I'll probably have you go and just watch those and sort of think about the material, and then any clicker questions that we have, we'll answer those on Friday when we come back. Okay? I'll also send you your quiz for Quiz Friday, or your assignment. They call it assignment on OpenStax, but assignment Friday, that doesn't sound nearly as catchy. So we'll keep calling it Quiz Friday. All right, you and your dog go for a walk through the park. On the way, your dog takes many side trips to chase squirrels or examine fire hydrants. When you arrive at the park, you and your dog have the same displacement. So you're walking at the park and your dog's going crazy, going all over the place. You have the same displacement. All right, we'll stop at 30. Okay, the answer is A, yes. You do have the same displacement. Remember, because displacement is only dependent upon your initial and final position. It's not dependent on what you do in between those two positions. And so you walk from here to here. Your dog, on the other hand, walks like that, but you have the same initial and final position, so you have the same displacement. Have you traveled the same distance? No. Obviously, your dog's traveled a lot farther. If the position of a car is 0, does its speed have to be 0? All right, I'll stop at 35. 35. Okay, good. Its speed does not have to be 0 at a position of 0. Good example. Let's say I have this pin, and I call this position y equals 0. Y is the up-down variable that we use. So I call this y equals 0. Now, when it's right here, it has 0 speed. But I can still call this y equals 0, but then pull the pin up here. This is still y equals 0, and now the pin is at like, I don't know, y equals 20 centimeters or whatever. But notice if I drop the pin, when it goes through y equals 0, it now has speed. So just because you're at the origin does not mean that you're not traveling. And we'll see that quite a bit towards the end of this chapter. Does the odometer in a car measure distance or displacement? All right, I'll stop at 35. 35. I think we'll probably do one more. Okay, that's awesome. A is right. That does measure distance. If it measured displacement, it would always go to 0, right? When you come home, your odometer would go to 0 when you pull into the carport or whatever. So a horse walks into a bar. Barroom jokes, okay? It's okay. A horse walks into a bar, and he says, "Hey bartender, give me a drink." And I'm sorry. The pony walks into a bar. Oh shoot! I already messed it up. Never mind. Never mind. Okay, all right. The pony walks into the bar and he says, "Hey bartender, give me a drink." And the bartender says, "What?" And the pony says, "Give me a drink." And the pony says, "What?" And or the bartender says, "What?" And the pony says, "Sorry, I'm just a little horse." Yeah. All right. See, it's not as much fun when you slug it up. All right. I think we might. Let's see. Is this an easy problem next? Yes, it is real easy. Okay. So does a speedometer measure velocity or speed? Does it measure the vector velocity or the scalar speed? All right. I'll stop at 28. 28. There you go. This is right. B is right. Y'all have a great day, okay?